Okay, number one, we've got an equation. They gave it to us, and the question says, how many grams of nitrogen dioxide are required to produce 5.89 kilograms of HNO3 in excess water? The first thing you have to do is figure out what even they're asking you. So the first thing is it says how many grams of nitrogen dioxide. We have two sets of nitrogens. Di means two. This one only has one. This has two. So this is what we're looking for. We're trying to find the grams of this element in our reaction. And it has given us this one at 5.89 times 10 to the third kilograms. We don't deal in kilograms. So the first thing you have to do is change this thing to grams. A couple ways you can do that is you could turn this into its normal number and move it 3 to the right. You can multiply this number by 1,000, which I think is just going to be the way I go here, and just turn that guy into a 6. And now we're dealing in grams. We want to go from grams of one part of this reaction to grams in another. But we can't talk in grams. We need to convert everything to, hopefully you're already like thinking in your head, like moles. We need to convert to moles. Yes, awesome. We're converting to moles. So the first thing we need to do is find moles of this one. Okay, so we've got hydrogen is 1.01. Oxygen is 16. We need 3 of those. Nitrogen, I think, is 14. Let's go to our periodic table. It is, 14. So we've got 48, 49, 59, 63, 63 grams over here. So that means this conversion factor is 63 grams to 1 mole. We're going to need this mole conversion, so might as well do it now. We're in our periodic table. Let's just find it. Okay, our nitrogen we know is 14 and our oxygen is 16 times 2. We can even put these together. This gives us 46. This conversion is 46 grams to 1 mole, or 1 mole to 46 grams. Remember, that's reversible. We can flip that over however we need to. Now let's get started with actually what we're doing. Okay, we start here with grams. 5.89 times 10 to the 6 grams. We're going to turn it into moles. We have grams on top, which means we need grams on the bottom. So we're going to put our 63 on the bottom and our 1 mole on top. Now we're doing the part that is called stoichiometry. It's using these coefficients to move between elements of our reaction. So we have 2 of these, and we're going to put that on the bottom because remember, we've got moles of this on top. We need to cancel them out. And 3 of these, nitrous oxide, nitrogen dioxide on the top. So that's a 3 to 2. So at this point in our equation, we are at moles of nitrogen dioxide. That's where we are. But we need to get to grams. So I'm just going to plug in that conversion right now. We have moles on top because this is grams. We got rid of grams. We're running moles all the way across now. If moles are on top here, moles need to be on the bottom over here. And the conversion of this guy is 46 grams. And then you should have your answer, which is 6.44 times 10 to the 6th. 6.44 times 10 to the 6th. And that's grams of nitrogen dioxide. Let's do another one. Okay, number 2. We have tungsten, that's this W right here, is metal is produced when we take WO3, we mix it with hydrogen gas, and we get water and tungsten. And we are given 1.0 times 10 to the 6th hydrogen. And it says specifically that we are in excess WO3, which means they're giving us as much as we possibly need. We're going to burn through a hydrogen before we finish our WO3. Okay. And they want to know how many grams of tungsten. We have pretty much a million? A million of grams of this, and they want to know how many million of that. How do we convert? We need to get to moles. So let's do that. 1.0 times 10 to the 6 grams of hydrogen. They have H2 here. That's just where we're at. So we need to get this into our mole conversion. This is 1.01. So the conversion on hydrogen, I'm running out of space to write it. I'm just going to write it right on the line. Grams on top, grams are going to be on the bottom. So that's our 2.02 for every 1 mole. Okay, now we are in moles of hydrogen. Now we can convert to our tungsten in moles. And this is where we use our stoichiometry, using our coefficient in the front. And for every 3, so we're dealing in hydrogen here, so we got to put hydrogen on the bottom so we can cancel that out. And we put tungsten on top, which is a 1. If it's not written, it's a 1, right? So now we're currently in moles of tungsten, and we need to get to grams of tungsten. So we need our periodic table. And I do not know this one. My goodness, I don't deal with tungsten very often. It is in the metal section. Looking. I think I wrote it down actually somewhere else. And 183.9. Ooh, 183.9. 83.9. And that's grams per mole, right? It's a 3. Oh, it just even got worse. Whiteboards. Okay, 183.9. So we're dealing with moles here. Our grams have canceled out. Our moles of hydrogen are canceled out. We're currently in moles of tungsten. So now we need to put moles on the bottom of tungsten. And we put our 183.9 on top to get to our final answer, which is 3.1 times 10 to the 7th of tungsten. There you go. Question 3 builds off of what we did in number 2. So if you kept some of those numbers or you wrote down answers as you went, you're a step ahead. If you didn't, you're starting over with me. But what I wrote is, here's what we started with. Our 1.0 times 10 to the 6th in our hydrogen gas. Our conversion of hydrogen to moles, grams to moles, is 2.02 grams per mole. So the first thing we need to do is get this hydrogen into moles to figure out grams of this one. Now they want to know, how many should we buy so that we're not having excess? How many should we react together to make this thing happen? So we're going to start there. 1.0 times 10 to the 6th. This is grams. So we're going to multiply it. We need to put grams on the bottom here and moles on the top. And then we use our stoichiometry. We use our relationship between these two, which is actually the same as hydrogen to tungsten, which is 3 of the hydrogens on the bottom and 1 of our WO3 on top. That's pretty good. And now we're going to multiply it over here because this is in moles of WO3. We need to figure out the conversion of this one. And tungsten itself is 183.9, sorry. 183.9, and we have our oxygen is 16, but we have 3 of them, so times 3. Let's not do this in our head, folks. Let's see. 16 times 3 plus our 183.9, and that gives us 231.9, and that's our conversion of grams to moles for WO3. And now we can put it into our equation at the end here. So we're in moles, so we're going to put our mole on the bottom, and we're going to put our 231.9 grams on top. And then we get our answer, which is 3.9 times 10 to the 7th grams. And that's of our WO3. Okay. Question 4, we've got CS2 plus 3Cl2. They already balanced this whole equation for you. They set you up with the reaction. The stoichiometric coefficients are filled in, which is really just 1. There's just a 3 right here. And they want to know, if you made 16 kilograms of carbon tetrachloride, how many CS2s did you use? How much did you need? Right away, hopefully some red flags. We don't work in kilograms. Okay, we got to turn this thing into grams. So you could do, we've talked about this. Can you even see that? King Henry died unexpectedly drinking chocolate milk. You're at kilograms. We need to get to grams. We go 1, 2, 3 to the right. Here's our spot. 1, 2, 3 to the right. We end up with 16 1,000 grams. Okay, that was step one. Next thing you should realize is we can't figure out carbon tetrachloride and get to CS2 with just grams. We need the conversion of moles. So let's go there. We have 16,000 grams of CCl4. We need to get that to moles. And how do we do that? We go to our AMUs. So for carbon, the AMU on that one is 12. And for chloride, it's 35.5. But we do have 4 of them, so we're going to need to multiply 35.5 times 4 plus 12, 154. That means 154 grams of this is in 1 mole of it. That's our conversion for carbon tetrachloride. This one we have grams on top, so we're going to need to put our grams on the bottom. And that's our 1 mole on top. This gives us how many moles of carbon tetrachloride we have. So we can do that number. That's not how I've been doing it for you thus far, but we can mix it up, right? We can learn a few different ways. And that gives us 103.9. 103.9 moles of carbon tetrachloride. So if we have 103.9 of those, now we can move. We can move within our equation. And we look at the stoichiometric coefficient is a 1. And our CS2, it's a 1. So we multiply this, seems silly, by 1/1. That's not too bad. But now we need to get to how many grams of CS2 we have, because by multiplying this by 1, we have 103.9 moles of it. Or we could call it 104. It doesn't matter too much, okay? Well, we can call it 103.904. We need to break this down. So carbon, we know, is 12, and we have our sulfur here. I wrote it down, actually, so I wouldn't have to go get it. But you'd look in your periodic table, and our sulfur is, oh dear, actually, I didn't write it down. 64.2. Nope. 31.1. My goodness, guys, you're being super patient with me. I'm just going to double check that I found the right number, because sometimes I just make stuff up. 32.1. Oh gosh, I was close. What a mess up here. Okay. 32.1. So then we double that because we have 2, and then we add 12 to that, and we end up with 76.2, I believe. 76.2. And that's grams in a single mole, or 1 mole of this is 72.6. All right, so now we're over here to finish multiplying this out. We can ignore the ones we got moles on top. So we do moles on bottom, put our 76.2 grams on top. And that gives us as our final answer of, because of significant figures, we have a 104 here, because I don't know if we were given ever more than, how many were we given? Let's look. Let's just do this. No, 16. We really only have 2 significant figures. So this is 100. That's silly. Sometimes if you just leave it in the calculator, you're going to get a slight variation. So if you looked at the answer key and realized, man, my number's a little different, that's probably why. You could have left that number in your calculator and kept going. They pulled it out and put it into the next equation, and they condensed it or found the significant figures. So that's how we ended up with 7.6 times 10 to the 3rd grams. If you were to do it longhand, like at least how I have 104 times 76.2, you could have had 7.9 times 10 to the 3rd. So if your answer is in between there, you're in a good place, which seems like a lot of room for error, but that's what rounding will do if you're rounding in the middle of your equation. Number 5, pretty wordy, and just looking at this equation, I mean, look at all that stuff. I couldn't fit it on the board, so I had to drop CaH4SO6 down. But let's read it together and break it apart. Number 5, to make a phosphorus fertilizer, and then in parentheses it says CaH4P2O8. So right now I'm gonna this is the fertilizer piece, okay? Because they look so similar, you could quickly be confused. Okay, that is our fertilizer piece. use the following reaction. And so here's our reaction, but the one thing I didn't write on here yet was the stoichiometric coefficients, how to balance this out. So we have 2 of these, 4 of those, and everything, and then 2 of these, and everything else is 1. So those other 2 big ones are 1s. Okay. If we have 2.5 times 10 to 3 grams of Ca3P2O8, so this is one of our reactants, not our product. We're making fertilizer, so we're going to put this in. This is one of our reactants. We're going to react it with excess H2SO4 and excess water. That means these 2 don't matter. This is the limiting reagent of this reaction. This is the one determining how much of the product we're making. We have these in excess. How many grams of fertilizer can be made? So we're trying to figure out how many grams of this one. Now, because we're not even going to do anything currently with the CaH4SO6, I'm just going to erase it. It still exists. It's still part of the reaction, but for space on our board and for simplicity, we're just going to erase it, okay? Grams of this, we want to know grams of that. And if you could just use the stoichiometric coefficient with grams, this would be so easy because it's a 1 and you'd say, it's the same, 2.5 times 10 to the third. But you can't. We have to convert to moles first. So let's convert to moles. Calcium, potassium, and oxygen. The only one of these I know off the top is oxygen. That's 16. So we need to go to our periodic table. Let's find what calcium is. 40.1. And we will be multiplying that by 3 and that one by 8. And phosphorus, we have 31. Okay, we got some big numbers here. I'm going to do this on my calculator because that is just too many things that we're adding together. 3 of these, 2 31s and 8 16s. That's going to get us to 310.3, and that's grams per mole. Okay. So far, so good. Now we're going to go start with these grams, 2.5 times 10 to the third grams. We're going to multiply that and convert it into moles. Because grams on top, we've got to put grams on the bottom. That's 310.3 grams for 1 mole. And this will give us moles of Ca3PO8. We're just going to keep going though and not give an answer. We're just going to keep plugging it in. If I see on your test or on your homework or on your work, all of these conversions all the way across, I'm not looking for the individual numbers pulled out. I'm looking for the process. Did you do the steps? Now, if you're just typing them into the calculator, it is so high likelihood that you're going to make a mistake because you're like, do I multiply or do I divide? But if I write this out, I see that I've got to cross off those grams. Okay. Next one is our stoichiometric coefficient. We have how many moles of this into how many moles of that. Luckily, it's 1. So all you'd write down is a 1-to-1. That was pretty easy. Okay. So now we're currently in moles of fertilizer, and we need to get to grams of fertilizer. We need to look at our periodic table. We've got our calcium, which we know is 40.1. Our hydrogen we know is 1.01. Our potassium we learned is 31. And our oxygen is 16. And now you multiply each of those by its subtext. So calcium you don't, that's just a 1. But hydrogen is going to have 4 of those. Potassium is going to have 2 of those. And oxygen is going to have 8 of those. So you're going to have a very large number, which I wrote down in advance because these videos are already plenty long for me, I'll tell you that. And we end up with 234.1. 234.1. This was 310. This one's even bigger. Isn't that crazy? Okay, 234.1. So this is moles on top. This is currently moles. So we're going to have to put moles on the bottom. And we put our grams on top. And we get our final answer as 189, 1.89, I guess, times 10 to the third. Now, do you remember when we said if we could just go across in grams, this would be 2,500 grams. And if we could just go grams to grams and use our stoichiometric coefficients with grams, we'd end up with 2,500, but we end up with 1,890. That's a significant difference. So if you're just guessing, it's not going to work. You've got to convert to moles and then do your coefficients and then come back to grams. And that's where we get our answer. And this is grams of fertilizer. Now, because these videos are so long, I'm going to take a break. You can take a break or roll up to the next video. I'm going to do 6 through 10 in the next one.